Welcome back. Today we're going to be studying 3.7 growth rate, interpreting functions. So when we have a population, we can model what could happen in two ways. We can imagine it's a line. The population goes up the same amount than what it up last year. Or we could imagine it as a jet, an exponential. If we imagine it as a line, that's the model y equals mx plus b. And if we imagine it as an exponential, that's the model a times x to the b, or rather b to the x. So let's write a model for the growth of the population in California in both as a linear function and as an exponential function. And then we'll compare that data to what actually happened in 1935, 1960, and 2010 in order to understand which is a better short-term model versus long-term model for modeling population. The California Population Project engineer in 1920 was tasked with finding a model that predicts the state's population growth. He modeled the population growth as a function of time in T years since 1900. Census data shows that the population in 1900 in thousands was 1,490, so that's 1,490,000. In 1920, the population of the state of California was 3,554, or 3,554,000. He decided to both explore a linear and an exponential model. So given the data provided, we want to study it as a linear function. So that's y equals mx plus b. Then we'll study this as an exponential function. Y equals ax, a times b to the x. We're going to do this both by hand and by spreadsheet. So if I want to find a model for these 2 points, I can imagine almost like an x and y graph. In 1900, since we're talking about years times 1900, t is 0, and the population is 1,490. 20 years later, in 1920, the population is 3,554. So I can imagine if I have this equation and I want to find the value or the model, I need to find the y-intercept, or the value where x or t is 0, where my input is 0. And I need to find my slope, or my change in my independent variable, in this case p, over change in t. Well, in this particular case, my function is actually pretty simple. I already know that in my 0 year, my population is 1,490. 20 years later, my population is 3,554. So if I take the difference of the two, let's see, that's 3,554 minus 1,490. That's 2,664. And the difference in time is 20. So my slope is something like 2,064 over 20 in terms of t. If I want to simplify that a little bit, then I can take my handy dandy calculator, divide the two, and I get an estimate of about 103.2 thousand people per year increasing in the state of California. So that right there is my linear model. Notice again, I need how much it was at t0, and I need the change in population over the change in time. However, if I'm going to do an exponential model, it's going to be a different type of calculation. I take, instead of trying to directly calculate the starting point and the ending point, I do this by substitution for the 2 points. For t equals 0, I say that my output has to be 1,490 for whatever a and b are when my input is 0. At t equals 20, or 20 years later, I say my output has to be 3,554 for whatever a and b are when t is 20. Now in this case, because anything to the 0 is just 1, this in turn simplifies to say that a, that parameter, that multiplier in my model, has to be 1,490. Once that I know that A is 1,490, I can in turn substitute it into here, thereby turning it into 3,554 equal to 1,490 times whatever B is to the 20th. Well, I don't know how to get that to the 20th, but I can divide both sides by 1,490 to get approximately 2.39 is equal to B to the 20th. Then I need a way of undoing something to the 20th. To undo something to the 20th, I actually raise it to the inverse. I would raise both sides to 1 over the 20th. So what we then have is 2.8 times the 1/20th, or B is equal to 1.04, which means our new model is y equals 1,490 times 1.04 to the t.